Hello everyone, today I would like to talk to you about the recent advances in single player performance of my Puyo AI. Let's see. So here we have Puyo playing AI. So this version is more than twice as good as my previous Monte Carlo version. This doesn't use Monte Carlo, it uses full tree search, which means that it takes the piece it's holding currently, which is falling here, and the next two pieces it can see, and then calculates all the possibilities that can come there. In addition to that, it takes the sort of fourth piece here, it is completely random, and goes through all the possibilities and all the choices it could make after that, and then decides what to do. And how it decides what to do is based on three different like signals or values or scores. One of the scores is this kind of group size here. You can see it's counting the groups right here for demonstration purposes. It finds 20-ish groups here of size 1, which are these little guys here, and it found 3 groups of size 2 and 9 groups of size 3, and it gives different scores for these. 1 point for each group of size 1, 4 for each of size 2, and 9 for size 3. So it really tries to maximize the size of the groups and number of the groups too, and you can see the total score calculated by that. The second heuristic it uses to calculate calculate how good the situation is by tracking the different chains. So it tries dropping each of the colors, single Puyos, on each of the columns, and then check what kind of chain would result from that. So we can see that there would be a green chain if you started here, and it would be a 6 chain. Then it found a red chain starting from here, and it would be like an 8 chain. There's a yellow chain and a blue chain currently, and then it calculates the efficiency. The most efficient way to chain is to use 4 Puyos per chain link, and we can see that these are quite efficient chains, at least 2 of these, and then there's the 7 chain that is not so efficient that it found. The third signal it uses is the actual score that it can achieve by actually blowing up these Puyos and starting the chain. I don't have a number for that because it depends on the tree search. It looks at all the possibilities, all the different varieties, and it chooses one of those that scores well in combination with these. Those tree signals have to be carefully calibrated for things to work. I'm not going to go into those details, but the final value that is calculated from that is displayed here. And this is the value that it finds after going through all of these different choices it could make for each of these next pieces and the ones that come after. So it's not the value of this current position, it's the value of the best position possible it can find looking at the current material. And let's see how much work it actually does per turn. So what we have is 5 colors, and those colors can form the single color pieces. Then we have 5 choices of the first color, 4 choices of the next, if we discount the ones that have only single color. And here it doesn't actually matter which color comes first. So if we have a piece with blue and red, it's the same as red and blue. So we divide those guys by 2. And that gives us 15 different deals, as I'm calling them. It's like dealing cards, you don't know what you get. Except here you do for for the next 3 pieces. And then we have the different choices that you can make. If you put your Puyo vertically, you get 6 choices. You can flip it around, which gives double the amount. And then you can put it horizontally. There's only space for 5 different ways to do that, and you have 2 of those. So there are 22 choices per move. And let's see how big the tree is. So you see 3 fixed deals per move. So that is already 10,000 positions to look at. And then you add the depth 1, which is all the random deals and all the choices for those deals. So you get 3.5 million different positions that the computer here is looking at for each move. And for each move it's checking, or it's like leaf here in the tree, search tree. It's looking at these chains, so let's multiply that in. So there are 6 different columns to start a chain from, and there are 5 colors to try to start a chain. And that is quite a lot. It's 105 million different pieces, or different chains that it's checking every turn here. And that's actually 350,000 different like leaf positions. I think I missed a factor of them previously. Alright, so it's doing quite a lot, and most of that parallelizes quite well. So it's using all of the processors available to do this, all of these calculations here. And let's see how it performs. You can see here that it has different groups of 3. It really likes those based on the group policy here, evaluation. So reds, blues, greens, reds, yellows. So we have 7 or now 8 groups in total. It also likes to make them into nice chains. So here we have, if the reds pop, it would pop the greens nicely in a group of 4, and the blues in a group of 4, and so on. So here it started a chain. The yellow and the reds, they were quite a big chain, wasting lots of material, but I guess that's okay for now. It would be nice to eliminate all of those, but that triggers templates so that it builds a good base for it itself. Like you can see here, this is no pattern I know of. I don't know any human players that would start their stack like this. So that's basically it, how it works. It does lots of computation and then chooses the best option it can find based on these evaluations. Let's look at like a couple of more chains and see if I can follow any of them. Like here, it starts this, it's green, yellow, purple. Does the blue hit? I'm not even sure. Like, it's not making this easy. It's doing quite complex things to build the chains, but they seem to work. There's active 10 chains starting from the blues according to it. What do we have? We have yellow. Okay. Did it start a chain? No. Okay, starting from here. Where does it find a red chain starting from here? Okay, now it goes purple, yellow into green, into yellow. Okay, that's a big hit, and there we go. A 12 chain. And yeah, quite hard for a human to follow, but much easier than what Monte Carlo does. So it already has some concept of how to do good chains, but not too much. Alright, I guess that's all I wanted to show you today. Next time we will see how we can make this do some multiplayer work. We're not going to do full multiplayer, but something towards it. So, see you next time.